There is one company on Earth that can build the machine capable of making the most advanced computer chip in the world. One, not five, not two. One company in one small country has held a monopoly on the single most important piece of industrial equipment of the 21st century for nearly 2 decades. And for years, Washington's entire strategy for staying ahead of China rested on that one fact. That strategy just hit a serious problem. According to a Reuters investigation, a team working inside a high-security laboratory in Shenzhen has built a working prototype of that exact machine, an extreme ultraviolet lithography system, the kind of tool the United States spent years and enormous diplomatic effort trying to make sure China would never get. The machine is reportedly generating the ultraviolet light needed to etch circuits onto silicon. It is not yet producing finished chips, but the fact that it exists at all has already forced a rewrite of how analysts in Washington, Amsterdam, and Taipei think about the next decade of the technology race. So did China actually get its hands on the most important machine in the world? Or is this something less dramatic than the headlines suggest? Tonight, we're going to walk through exactly what this machine is, what China has actually built, what it hasn't, and why the answer to that question may matter more to your daily life than almost any other story in technology right now. Here's why this isn't just an industry story. Every advanced computer chip that powers your phone, your car, the data centers running artificial intelligence, and the guidance systems inside modern weapons depends on a manufacturing process called extreme ultraviolet lithography, or EUV. Since the technology became commercially viable, exactly one company has been able to build the machines that do it, a Dutch firm called ASML. For most of the last decade, Washington's approach to slowing China's military and technological rise has depended heavily on making sure that single supply chain never reached Chinese factories. If that choke point is starting to crack, the implications reach into the AI race, into defense planning, and into the price and availability of the electronics Americans buy every year. My name is David Whitmore, Chief International Analyst for Breaking News Analysis. Tonight, we're breaking down what China has actually built, what the experts disagree about, and what this means for the balance of power between Washington and Beijing. Let's get into it. To understand why this machine matters so much, you need to understand what it actually does, because the physics involved are almost absurd. An EUV system fires a high-powered laser at a droplet of molten tin, roughly the width of a period on this screen, tens of thousands of times per second. Each strike vaporizes the tin into a plasma that gives off extreme ultraviolet light, a wavelength so short that ordinary lenses can't even focus it. That light gets bounced through a series of mirrors polished to a level of precision so exact that, scaled up to the size of Germany, the tallest imperfection on the surface would be a few millimeters high. The light finally lands on a silicon wafer, etching transistor patterns just a few atoms wide. A single ASML machine can cost between $150 and $250 million, depending on configuration. It's built from more than 100,000 individual components, sourced from a specialist supplier network spread across multiple countries. ASML itself has said it invested more than 6 billion euros, roughly $7 billion, over 17 years to get this technology to the point where it could be sold commercially. Chip War author Chris Miller has pointed out that the roughly 3 decades of global research required to build the first commercial EUV system is exactly why so many analysts assumed China's own path to this technology would take decades, not years. That assumption is now being tested. According to the Reuters reporting, the Shenzhen prototype was built by a team that includes former ASML engineers, and it relied heavily on reverse engineering, using components salvaged from older, second-hand ASML machines purchased through intermediaries on the secondary market. One economist quoted in coverage of the story, Gary Ng of Natixis Corporate and Investment Bank, said that if the effort effort succeeds, it would massively increase China's geopolitical leverage over the United States, and noted that mastering this technology has clear defense applications, not just commercial ones. It's worth pausing on how China got even this far, because the path matters as much as the destination. Part of the progress has come through what analysts describe as talent poaching, hiring away engineers who once worked on light source technology and precision optics at ASML and at the German optics firm Zeiss, which supplies ASML's mirror systems. A team at the Shanghai Institute of Optics and Fine Mechanics, led by a scientist who previously worked on light source technology at ASML, reported a breakthrough in laser-produced plasma back in March of last year. Chinese researchers have also pursued a genuinely different technical approach in places, refining a solid-state laser design for generating the light, a method ASML actually tried and abandoned years ago because it wasn't efficient enough for mass production. Some Chinese teams now report a conversion efficiency approaching the threshold that would make that older method viable again, using cheaper components than ASML's approach requires. So, if the light source problem might genuinely be solvable through a different technical path than the one everyone assumed China would have to copy, why are so many serious analysts still skeptical that this changes very much, at least for now? Because building a working prototype and building a commercially viable industrial tool are two very different achievements, and the gap between them is enormous. A more recent independent assessment published this month lays out 3 specific technical hurdles China still has to clear, which give us a genuinely useful way to track real progress instead of relying on press releases. The first is light source power, actually generating the EUV light at a strength high enough to manufacture chips at commercial scale, not just in a lab setting. The second is mirror smoothness, the almost impossibly fine polishing tolerance needed for the optics to work at all. The third, and perhaps the hardest, is photoresist purity, the chemical coating on the silicon wafer, which needs to be manufactured with impurity levels measured in parts per billion or even parts per trillion. China is described as only in the early stages of research on that third piece, though a team at Tsinghua University did announce a promising lab-scale breakthrough in a different photoresist formulation than the one Japanese suppliers use. There's also a second, separate Chinese effort worth understanding, because it shows Beijing isn't betting on just one approach. A domestically developed machine known as Shiji uses an entirely different technology called electron beam lithography, which draws circuit patterns directly onto a wafer with a focused beam of electrons rather than projecting light through a mask. It's flexible, and it doesn't require the costly photomasks that traditional lithography needs for every new design, but it's also far slower, tracing each pattern point by point, rather than exposing an entire pattern in a single flash of light the way EUV does. Independent analysts at the Center for Strategic and International Studies have described Shiji as heavily promoted in Chinese state media, but in their assessment, unlikely to have much practical commercial payoff, and they've cautioned that China's technology announcements should generally be read with some skepticism, given how the country's state-directed funding model tends to produce a lot of parallel projects, many of which end up technically unviable, even when they generate impressive headlines. Here's what the skeptics and the more alarmed analysts actually agree on, which is more informative than where they disagree. Even in the most optimistic reporting on the Shenzhen prototype, China has not yet produced a working, market-ready chip using this machine. Reuters sourcing describes an internal Chinese government target of having working chips by 2028, while other analysts covering the story think 2030 is a more realistic date for anything resembling mass production. In the meantime, China's leading chipmaker, SMIC, continues to rely on older deep ultraviolet machines and a workaround process called multi-patterning to produce advanced chips without EUV at all. That approach works, but it's expensive. Reports on SMIC's costs put its expense per finished wafer somewhere between 40 and 50% higher than what Taiwan's TSMC pays using EUV directly. And SMIC's yield rates, the share of chips that come out usable, are reported to be below 50%, compared to yields well above that at the industry's leading edge. So even if the machine itself works exactly as advertised, mass production is a completely different mountain to climb. Yield, uptime, throughput, defect rates, all of that has to come together at scale. And history shows that gap can take years to close even once a working prototype exists. That raises the real question underneath all of this. Does a prototype that isn't making commercial chips actually change anything today, or is its significance almost entirely about what it signals for the future? The honest answer is probably both, and here's why. Strategically, the existence of a working, domestically built EUV light source changes the ceiling of what's possible for China, even if the floor, actual chip output, hasn't moved much yet. For years, the entire architecture of American export controls rested on a genuine technological monopoly, not just legal restrictions. Washington worked with the Netherlands, Taiwan, Japan, and South Korea to build a coordinated set of controls specifically targeting ASML's ability to ship EUV systems to Chinese foundries, on the theory that China simply could not replicate the machine on its own within a meaningful time frame. If that technological floor is cracking, even slowly, the entire premise behind that coalition of export restrictions gets weaker over time, regardless of how long full mass production actually takes to arrive. There's an economic angle here, too, that gets less attention than the national security story, but may matter just as much to ordinary consumers. Some analysts covering the semiconductor industry argue that even before China masters EUV, its growing base of older DUV-based chip capacity, subsidized heavily by the state to keep companies like Huawei competitive despite higher costs, could let China capture a substantial share of the world's lower-end chip market by the end of this decade. If Chinese-made chips flood that market at prices Western manufacturers can't profitably match, car makers and appliance makers under real cost pressure may find those chips hard to resist, whatever the geopolitical implications. That's a very different kind of competitive threat than a race to the most advanced node, and it's one that could show up in ordinary consumer prices well before China ever masters full-scale EUV production. None of this happens in a vacuum either. ASML's own public response to the Reuters reporting was notably measured. The company acknowledged in a statement that it makes sense other companies would want to replicate its technology, while adding that doing so is no small feat, a fairly understated way of saying that a working prototype and a mass-producible industrial tool remain very different things. It's also worth remembering that this isn't the first time ASML's intellectual property has ended up at the center of a dispute with China. Back in 2019, the company won an $845 million judgment against a former Chinese employee accused of stealing trade secrets, a reminder that the boundary between legitimate reverse engineering and outright theft has been contested territory in this industry for years already. So let's connect all of it. Has China gotten its hands on the most important machine in the world? The most accurate answer, based on what's actually been reported rather than what headlines imply, is partially and provisionally. China has demonstrated that it can generate the extreme ultraviolet light at the heart of the process using a mix of reverse engineering, recruited talent, and at least one genuinely original technical approach that ASML itself once tried and set aside. What China has not demonstrated is the ability to turn that light source into a reliable, high-yield, commercially viable manufacturing tool that can compete with ASML's decades of accumulated engineering across mirrors, photoresists, and production-grade reliability. The winners and losers here are more layered than a simple two-sided race. Beijing wins strategically just by narrowing the psychological and technological gap, even without full mass production, because it weakens the credibility of the export control coalition the US built with the Netherlands, Japan, Taiwan, and South Korea. ASML, ironically, may not lose as much in the near term as people assume, since the gap between a lab prototype and a reliable industrial tool remains wide, and the company's decades of accumulated expertise in yield reliability and the surrounding supply chain aren't easily replicated, even with a working light source. The clearest potential loser, if China's lower-end chip strategy plays out the way some analysts expect, may be Western manufacturers of everyday electronics and appliances who could face serious price pressure from subsidized Chinese chips long before the more dramatic, headline-grabbing EUV race is ever actually settled. Analysts genuinely disagree about how fast the rest of this timeline moves, and that disagreement is worth taking seriously rather than resolving artificially. Some see a 5 to 10-year gap still separating China from a truly competitive EUV industry. Others argue that the pace of the last 18 months from a single laser efficiency breakthrough to an operational prototype suggests the gap could close faster than almost anyone expected even a year ago. Both views are being argued in good faith by people who study this industry closely, and the honest answer right now is that nobody, including the companies and governments most directly involved, knows for certain which timeline is correct. 3 things are worth watching from here to see which version of this story is actually unfolding. First, whether China's photoresist research, the area experts consistently flag as furthest behind, produces anything that moves beyond a lab result and into an actual production line. Second, whether SMIC's yield rates on advanced chips start closing the gap with TSMC, since that would be the clearest sign the broader ecosystem around any future Chinese EUV tool is maturing, not just the light source itself. Third, whether Washington and its allies respond to this prototype by tightening export controls further, or whether they quietly acknowledge that the technological monopoly the whole strategy depended on is no longer as absolute as it once was. The machine that runs the modern world was supposed to be the one piece of technology only one company on the planet could build. That's no longer entirely true. Whether it stops being true in a way that actually matters, on a factory floor producing real chips at real scale, is the question that will define this rivalry for the rest of the decade. If you found this analysis valuable, subscribe to Breaking News Analysis for in-depth reporting on the stories shaping America's future. I'm David Whitmore. Thank you for watching,